tutorial, and Professor Howard will interact and he will discuss about lactase enzyme. So it's free, it's open for everybody.
Welcome all in this session, and I think this will be a very interactive session and based on the research experience of Dr. Lee. And by the time we start the session, you should also try to note down your queries because sometimes we are having some spare time so we can discuss. We'll try to have this session at least 15 minutes we get early so that we can have the visits to some these experimentations where real experimentation is going on or any other discussion which we can do that. So I request Dr. Liu to kindly start the tutorial session. Okay, no problem. So by the time we search the tutorials, I just want have some queries about that whatever learning we have done today about the CBP. So any of you they have known about CBP binding modules which are there in bio, how the CBP is generated? Anybody has searched this literature? Or do you have studied in detail about the structures? Like you are trying to break the xylem. So what is the structure of xylem and what is the complication? Why people are working on that? Even lignin.
Okay, in the tutorial this afternoon, I like to introduce something about the lignin.
Yes.
Including a new concept about lignin consolidated part processing. And some results from my work about lattice. Lattice is a lignin degraded amide oxidase. Okay. First, let's take a look at the structure of lignin. Lignin is totally different from polysaccharides. For any polysaccharides, there are repeat units. There are monosaccharide units. But for lignin, it's much more complicated. First, let's say, is it consists of three different types of phenylpropanes. The first one is coumaryl alcohol, coniferol alcohol, and synaptic acid alcohol. These three different alcohols. The difference is here, is this group. And for different plant species, the content of these different of these three phenylpropanes is different. These structure connected with these units connected with each other. Okay, so different covalent bonds, including carbon, oxygen, carbon bonds, we name it as beta O4. Beta is here. This is alpha, beta, gamma. This is beta carbon, beta O4. 4 is the first carbon in this ring. 1, 2, 3, 4. So the beta O4 structure is a representative structure. It contributes over half of the linkage in the lignin structure. Other important structures are alpha O4, alpha over here. If the bonds connect with the alpha carbon. And we also have beta 1, beta beta, 5, 5, and 405. These different structures. The The lignin consolidated bioprocessing is based on the degradation of lignin. First, the lignin should be depolymerized. The structure, the molecular structure, the huge macromolecular structure should be broken down into small molecules into low weight molecules, usually composed of aromatic derivatives. And we use another microwave to uptake all of these organic compounds and produce carbon in the form of PHA, wax esters, and other useful compounds. And it can also produce energy from this process. For the first process, the polymerization of lignin, we have white rod fungi. It has a lot of different oxidative enzymes, including lipase, the lignin oxidase, and manganese oxidase, and peroxidase, and the volatile peroxidase. They work together to depolymerize lignin into a low molecular weight, small compounds. And in the next step, we have some bacteria. From the literature, we can find a lot of different bacteria. They have the pathway, catabolic pathway proceed via the oxidative ring opening of the central aromatic intermediates. The central ring is here. It's this way. So, especially this one, this way. Okay, what we are going to do is to look for bacteria that possess these catabolic pathways. Here I show some results from this author. They finished this work 3 years ago. They isolated microwaves from environmental samples. These different spots representing the different samples, samples. And the orange one is nitrogen limited, and this one is nitrogen sufficient. From this screening, they get some several strains that can be used to CVP of lignin. Finally, they characterized the products. They found that some can produce ferulic acid, produces vanillic acid. Although the production level is not high enough, but this result can attract much attention to us because it's a new research direction. The CVP of lignin is relatively longer than what we need, what we are doing to compile it. Usually over a week for the treatment. Now I have 2 questions for discussion. The first question is, in the next step, we can try to develop an integrated consolidated bioprocessing for the whole components of biomass. Because we have a CVP microwaves for cellulose, for hemicellulose, and now maybe we can find a very simple one, very simple for the CVP of lignin. So can we integrating them together, integrating the processing of the whole components of biomass together? And how can we screen and engineering these microwaves? Second question is it good? Maybe these microwaves, if it is successful, it will cause ecological disaster because it eats the wood, the grass very fast. So it may change our environment, change our campus, change our living environment. So maybe it is not a good thing. Okay. So can we discuss these 2 questions?
Yes.
Do you have have any plan to start this? For example, we combine the consolidated the data to file processing degree and with policy practice together. Is it easy?
Everything is common.
Yes.
Yeah.
It's challenging.
Yeah.
But
Because the ability to degrade things and is with certain organisms and the ability to degrade the polysaccharides is with other organisms. But integrating everything together
yes.
that's a big challenge.
And those are all bacterial enzymes. So the last event. Those are all bacterial enzymes.
Bacteria.
And the last lecture. These are all bacteria.
This
Any residue, no residue.
no.
And residue has a capability of getting better than yeah. Because most of the enzymes, they are all intracellular. They are not extracellular enzymes. They are not situated outside the cell. They are bacteria.
In case of bacteria,
Most of these enzymes, like talking about ligand enzymes, they have to take this. So how can we do it naturally? Natural way of doing it. Because in soil sample in nature there is a succession. One of these dies and cell wall degrades, or if they are cell wall degrades, or another it's a food for other micro. There is succession going on. Succession for living degradation. So there is a exposed living to be degraded, another micro will come and will utilize the leftover cellulose and cellulose. Then another will come and they will utilize the sugar. So there is no succession. If you could mimic the succession in artificial way in lab, then only it is considered bioprocessing process. We could study, if we could observe that in nature naturally, how nature remains or removes substrate is degraded. Because in any tropical forest, you see any tropical forest, radiation is very fast in tropical forest. Yeah, so there are a lot of bacteria and fine ASCO and bacillus and even detroit. So, but this study is on bacteria and bacteria. So you will have some limitations.
It's feasible with a consortium of microbes. If we develop a consortium, so selected microbes, they can live together. They can be used.
And time will be constrained. You can't control the time.
Yeah.
Because in normally when we do externally, the bioreactor, we know that in 12 hours before the whole experiment will finish. So here, how can we control time? It will take like the mushroom cultivation you told. It takes you take 7 minutes every direction and
It's important for you to digest the components of biomass. I mean, it's also important to produce the useful products.
yeah. So in biorefinery concept or biorefinery, this is very nice, very
Very good.
yeah.
Yes.
Because they can get other valuable products, byproducts of lignin. Yeah.
And I think the students should also learn this is very good presentation, you see, and presenting the data in this way, that is really very attractive. Yes. Miss anybody? Yes, yes, very good then.
This is known as, you know the presentation form, what do we call this now? What term? What do we call it? What do we call this form?
What kind of the chart it
You
is?
can see there is a variation from light blue to green, light green to red.
What is this type of data presentation is
It's very
called?
nice here. You don't have to put values. It's a heat map. You can draw using Excel. Heat map. If you want large number of data, normally we use this form.
But these days it is used.
This is
Yeah.
this is can use this.
Okay. Okay, let's move to the second part. I start from the modeling of important lattice. This lattice has a commercial name. It's Nozyme 51003. You can purchase it from Sigma Outreach. Sigma Outreach, there's a commercial name. This commercial name is preserved. And it is a formula like this. It is from this strain. It is hemophilia strain. So it's hemophilia from that.
Sigma cells release.
Yes, it is for production of this lactase, it is the gene expressed in aspergillus. So it is aspergillus expressed, but the gene is from this one. And we can get the gene sequence, the DNA sequence of the lactase from the database, from the SBI database. We can get it. But I looked up to the patent, the published patent from online. In the patents, you provide the original sequence of this lactase, slightly different from the NCBI database information. So, with the help of Dr. Kunit's name, I did the homology modeling first, use online survey. After the modeling, I get like this structure, like this, a three-dimensional structure, and it has four important active sites. These are copper ions. The copper ions represent for the oxidative and redox reaction phase. This reaction sites. And there is also a chloride. The red one represents oxygen. So this enzyme first uptake oxygen and converts oxygen into water, and there's electron is transferred, and substrate. We have a phenolic substrate. Will be oxidized to radicals. The radicals then can be converted into dimer or can be degraded. Here we find the active site, active pocket. We propose that all the substrates can enter this active site, and we also did the approach. All the amino acids in this model seem very reasonable. Then I tried to use the liquid model compounds. We have a lot of different liquid model compounds, of compounds. We have a monomer. I present 6 monomers. The first 3 monomers are all alcohol. They are all alcohol. Then the next 3 monomers are it has a carboxyl group. It's acid. Next is a dimer. Dimer is it has 2 monomers valently linked together with ether. And we also have a trimer and a tetramer. Tetramer is very big molecules. We cannot get the 3-dimensional structure from the database, so I use another software. Well, it is ChemiOffice. ChemiOffice has a new function and can help us to build up the 3-dimensional structure of small molecules. So after the preparation of the modeling of the lactase and the preparation of the modeling of ligands, I tried the autodock. Docking of ligands into the lactase active site. I found that all of the ligands can enter this active pocket with the binding energy. on the end lowered with molecular size and molecular weight. There is a higher molecular weight, and the binding energy is lower. And for the tetramer, since this molecule is too large, it cannot enter the active site. So I will propose that this lattice non-line lattice cannot catalyze the oxidation of this tetramer because of it does not have enough space.
This tetramer, what is the monomeric unit sign?
Yeah, yes. This tetramer is derived from monomers. This tetramer is reasonable. We get it from United States. There's a database. It has been published. It has also been synthesized from the enzymatic roots.
So the fact that we clearly read that package can degrade lignin. So does that mean, because here you are showing that it can only, the monomeric unit or the dimeric unit can only enter the Hooke's catalytic site. So how do we justify the statement that lignin package is a lignin degrading enzyme?
Yeah, first for efficient degradation reaction, because lignin enters the active site of enzyme is very important. Not always for lignin, for lattice. If we have a mediator, if there was no molecule for transferring its electrons, it's not a problem. Okay. Yeah. Although they cannot bind with each other, it's not a problem because we have a mediator. But actually, the tetramer is much more difficult to be degraded, not only because of the molecular weight, but also because of the exposure of phenolic group. Phenolic group is very readily to be oxidized by lattice. And then I tried another experiment. This experiment solves a problem about ionic liquid. Yeah. For ionic liquid, we tried a lot of a series with different alkyl chain lengths. Okay, this has two carbon. This has 4 carbon, 6 carbon, 8 carbon, and 10 carbon. So please guess which one is the strongest inhibitor to lattice. Which one will be the strongest inhibitor? This one or this one? Many authors mentioned that okay, the inhibition capacity of ionic lipids to enzyme to protein depends highly on the alkyl chain length. This one has the strongest inhibition factor. And we also prepared the substrate. We use ABTS. I will mention ABTS many times because it is very important to the lattice research. And I also use a DMP. DMP is another substrate commonly used for lattice activity. And GIAN. In the first step, we studied the inhibition. We studied the inhibition using conventional ways. Use line Weber Burke blocks. It's derived from the animal patients, right? we test the activity of lattice towards a specified substrate with a different content of ionic liquid. Then we can plot the reaction velocity with the substrate content. But we transfer it in the form like this. So from these plots, we can find there is a very important spot on the y-axis. It tells that the inhibitor may be a competitive binding mechanism. And here we use another salt. This salt is potassium chloride. And this is the EMIM, and also in the form of chloride. See, they are different. They're different, yes.
So please elaborate both the graphs. We are not getting. One side there is a point, you mean they're coinciding at one point means there is inhibition.
Inhibition, yes.
In the first graph.
Yes,
And
first
in the
graph.
second
This
graph,
one,
they're
this
not
one.
coinciding at y-axis.
Yeah, this is also, there is also inhibition, but it's
This is
very
not
complex.
competitive inhibition.
Huh?
This is not competitive inhibition, that is competitive.
Yeah, it is a very complex mechanism. Maybe involves competition, competitive inhibition, or non-competitive inhibition.
What do we interpret from these two graphs?
Different. They use different salts.
Okay.
Different salt. This salt is very common. It's inorganic, but this salt is organic.
These salts are to inhibit lactase.
Yeah, two inhibitors of lactase. They are all inhibitors. Even the sodium chloride, potassium chloride, yes.
And these bottom graphs, CD.
Yeah, in the C and D, in these two figures, we calculated the inhibition index. And we also calculated the initial velocity. We do the initial velocity. And we found that the actual chain length, the higher the chain length, the inhibition, the stronger inhibition.
These can be plotted in Excel only.
Uh-huh.
In Excel, Microsoft Excel, or you have used some software for these graphs.
How did you plot this graph? How did you make this graph?
How did I make it? I use Origin software.
Origin software.
Origin software, yes. It's not very easy.
But it is very similar to Excel. But graphs look beautiful in Origin. Yeah.
So for a competitive binding, it means that the inhibitors irreversibly occupy the specific binding sites for substrate. And for an inline inhibitor complex, it means the ionic liquid maybe enters the active site of lattice and committed with the normal substrate molecule. And there might be a complexation between the enzyme and the inhibitor. So in the next work, we are going to prove these two assumptions. We proved the first assumptions that there is a new complex formed between the lattice and the ionic. And from the UV visible spectrum, the blue line is the pure ionic liquid, and the red line, this green line, is the lattice. This lattice is also pure, no other chromos. Since they have a different absorption band, especially lattice, it has a shoulder around the 270 nanometer. But if they were mixed together for a while, there is a complex formed, and the sugar, and the big shift to the right direction. So the spectral method can help us to characterize the newly generated complex from lattice and our liquid. And the red shift means what? Red shift means from the absorption peak. It means the complexation absorbed energy. It requires energy to form the complex. Then we also use the autodock to simulate the docking of ionic liquid into the active site of lattice. We got five pictures for different ionic liquids. They have different alkyl chain lengths. They have all of them can enter the active site and bind with lattice. So from the ABTS and the ionic liquid, we can find that they are competitive relationship. Yes. Then we calculated the binding energy and the alkyl length, and we studied the correlation. We found that the binding energy is it is not always decreased with the chain length. In the next step, we studied the optimal pH of lattice in the presence of ionic liquid, and we found that yes, ionic liquid shifts the optimal pH of lattice considerably shifts. So if you are going to use ionic liquid, only its content is not 100%, its content is 10%. You must take into consideration the optimal pH of lattice shift. It will change because they form complex like this. We use DMP as DMP glycol and SA as substrate, and we use a buffer. We compare the buffer and ionic liquid. We found that for them they have different optimal pH, and especially for DMP, it has two optimal pH. Can you help me explain this phenomenon?
These are also purchased from Sigma, DMP and
DMP is these are all substrate for lattice.
yeah, they are purchased from which company?
Which
Which company you are purchasing these
okay,
capsules?
Sigma, of
From
course,
Sigma.
yes, Sigma outreach.
So how do you interpret two optimal pH?
Yes, we don't know why there is two optimal pH.
Is it the enzyme of pure preparation? The enzyme you're using is it a pure preparation?
It's from Sigma. We consider that it's high purity.
No, that lattice is also from Sigma.
Sigma, yes. All it is produced by an enzyme, but it's a Sigma product.
And what are these dashed lines and dotted lines in buffer and ion liquid?
That, excuse me, dash line
Dashed lines and straight lines.
and straight line.
Yeah.
The straight line is from buffer. We do not add the ionic liquid in. But the dash line from ionic liquid is also buffer. Yeah.
This will show the effect of ionic liquid.
Yes.
That is why we are using buffer as a control.
If you read publications, you will find about the effect of ionic liquid on enzyme. The different group will give different results.
Yeah.
Someone tells that okay, it's inhibited. Someone tells okay, it stimulates the activity of lattice. And we explained that because of the shift of optimal pH. And why it shifts? Because of the formation of complex. Yes.
So this data is published?
Published, yes. The most interesting part is here. Okay. We compared a lot of different salts in organic, including the buffer. The buffer is a phosphate buffer. Phosphate buffer. There's a phosphate and a citric, and the citric acid. Okay. Phosphate. Phosphate. Yes. We are citric.
Phosphate buffer.
Yes.
And pH of this buffer is?
Yeah. There's phosphate buffer. The enzyme, the lattice is very stable with increasing concentration of salts. Very stable.
pH of phosphate buffer?
Yes.
What is the pH of phosphate buffer?
All of them are at pH 5. But different cells of treatment use different pH.
Yeah.
This one is from ABTS with pH 5. See, the first line, this green dash, is from the buffer, phosphate buffer. And these two from potassium sulfate and EMIM sulfate. There are no big difference. So it's another problem. Okay.
Normally we use citrate phosphate.
Yes.
We use citrate and phosphate.
Citrate.
Citrate phosphate.
Yeah, this is from citrate and phosphate. Phosphate, citrate.
Citrate.
Yes.
Phosphate citrate.
Yeah, citrate is acid and phosphate is salt. Prepare this buffer in enough place.
Citric acid and the conjugate base. Phosphate is the conjugate base.
With increase in concentration of the salts, the activity is decreasing.
Yeah, activity decreasing. But the phosphate stable. And the sulfate less stable, but it's also okay. And for the chloride or acetate, no. So we said that the inhibition is highly dependent on anion.
Yeah. Yeah. Totally dependent on an ion.
Question? So finally, we proposed a cumulative mechanism of the inhibition.
Sir, 1 minute. Previous slide. So what is this Hofstadter series? Can you explain it?
This series is a cumulative mechanism. It tells that the inhibition capacity for the salts to protein follows a rule. The rule correlates with anions and also correlates with cations. It's a theory, but not widely accepted. It's a theory. It is result to support this theory. Yes, we discussed it.
Is a series in like decreasing order or increasing order?
Yes. Yes.
Okay. Okay.
So finally, we proposed mechanism. We concluded the results that first, ion lipid is an inhibitor because its cations can uptake the active sites of lattice commutative normal ligand, normal substrate. But the anion is also very important for the elevation effect. This work is about the recovery of the mediator. Like this is very good. It's a captive in line, but its capacity for the biodegradation of contaminants in the environment highly depend on the use of mediator. The mediator ABTS. This is ABTS. It's very expensive. Very expensive, and it's not stable. I will explain that. In this work, we are trying to recover ABTS after use, after it turned from slight blue to dark blue. Then we try to turn it back. Okay. We use acetone. First, we study the inhibition of acetone on lattice. Acetone is a solvent. This solvent is evaporates very fast. Evaporates very fast, and it dissolves in water. And they can they are competitive with each other. Also, we tested the constant, the kinetic constant. That is, aqueous solution of different acetone contents. Different content. The substrate we used is ABTS. The ABTS, its original form is the color is very light, almost no color. But after oxidation, it turned to dark blue. It is a form of cation radical, cation molecule radical. It is a radical, and it has a electric charge, positive charge. Yes. So we tested the K, the VMX, and the efficiency of the inline on different acetone content. We found that our inline cannot stand very high acetone content. Then we try to explain it. Also, we studied the UV visible spectrum of the ABTS radicals. These radicals is produced by inorganic oxidants, not by lattice. And in this system, there is no lattice, only the ABTS radicals. It is well prepared. Okay. Its UV spectrum is like this. It's like this. It has absorption at the wavelength 420 nanometer. Then we add the acetone in a few seconds, in a few minutes. Okay, in a few minutes the absorption decreased. Then in 1 hour, decreased to 0. No absorption at all. But the absorption for the original form, for the ABTS original form, the reductive form, okay, the peak is here, it's around 345. Then this peak rises because of the presence of acetone. So the result is that the addition of acetone in the ABTS radicals turn these radicals back to the reductive form. Am I right? But why? Why? We propose that the ABTS radicals is oxidative radicals. It can oxidize the acetone.
And acetone is inhibitor of lattice.
Am I right? I don't know. I don't know. I did not do further study about this.
It seems like a story, this slide. this happens, then this happens, and ultimately peak done.
The UV visible spectrophotometer we use angular. It's very good. It can take a record of the spectrum every 5 seconds, or even every 3 seconds. You get a lot of data. Yeah.
You need to take the reading or automatically,
Yes.
in the system it is giving you reading after regular intervals of time.
Yes.
Regular system is automatically giving the readings
Yes.
for absorbance.
Yeah.
Which spectrophotometer you are using?
Angular.
Excellent.
8453.
8453.
Yes.
8453 R.
A. 8453 A.
8453 A.
A. Yes.
So what is second graph?
The second figure is a decrease in few minutes at a very high content of ethanol, 80% ethanol. In a few minutes, in 3 minutes, the ABTS radicals was scanned. So the ethanol plays a role of anti-oxidative agent. Let me start with the scavenging of ABTS in a various number of different water miscible organic solvents. Lots of different. First is acetic acid. No, stable. No reduction. Stable, very stable. But in methanol, it's also stable because it's 90% degree reduction requires 6 hours. And for ethanol, also requires several hours. But for this one, dioxane is also commonly used in bioorganics. It's very fast, much faster than ethanol. And next, we are going to use this ethanol solvent to recover ABTS from the reaction system, and we find a new thing, a new structure. First, this one is original radical. It's the original radical at 420. The absorption rate. And if we recycle it for one time, we found that the total ABTS radical decreased, a portion lost. Yeah. And if we just recover it for seventh here, we got very few ABTS radicals. So the ABTS radicals reacted with acetone, but finally, it is converted into another structure. So how can we explain these results? See, it's here. We proposed that we have another form of ABTS. This ABTS is a dication ion. It's not a radical. It's the final stage of ABTS after 7 recycling. And for the first time, we get this UV spectrum. We found it's not red. Its color is like this. Its color like this. And then we used the ability test for recycling. We found it totally 4 times the recycling. Have question? We have deep discussion. I'm very familiar with Linux and some other enzymes. Yes. But I'm not very familiar with metabolics. Metabolics is somehow too difficult for me. Question?
Yeah, a lot of questions.
Okay, we can discuss that.
Can have one. Can have one. Okay.
Please.
We racing purpose we normally use Wi-Fi, which is much cheaper than LPS. So when you use LPS as a mediator, it is also substrate for racing. Yes, so it is. So when you mix up with package enzyme, color changes into greenish, slightly bluish gray. Yes. Greenish. Greenish. So when we use LPS as a mediator for any reaction, so what about the value when you recycle because it is why do we recycle it? Because it is very costly or some other purpose?
Yeah, very possible. Yes.
You want to recycle it. So how do you verify that? After recycling, you need to verify. After recycling, the acetone method, use acetone for recycling.
Yes.
How do you verify that? Because it's a very small molecular weight molecule, very small. So because verifying protein is so tough. How do you verify every cycle? Because you need to verify it after recycling. Then again you have to reuse.
Yeah, it's a very big problem. I use ultra filter. Ultra filter, I purchased a centrifuge tube, and the centrifuge tube there is
Ultrafiltration layer is a fake.
yes.
It's what size? What is the
It's not difficult for the separation. In my experiment, like this cannot
Membrane
pass membrane.
yes. But acetone will pass. Acetone and mediator will pass to the membrane.
Yes, it's not. We can. We have another way. We can force the evaporate.
Will go for acetone.
With vacuum conditions, we evaporate the acetone first, and then we do the.
Concentrate.
So there are reports of natural mediators. Do you have any idea of how are there some natural mediators?
Natural mediators is like this. It's not cheap. It's not cheap. Most of the natural mediator is derived from this basic structures. As it is oxidized by lattice, the H electron lost. Okay, there will be radical forms. These radicals can combine with each other, form the cross-linked dimers, trimers, and or even tetramers. I have some data about the polymerization. Natural mediator tend to form a lot of different oligomers.
So these are they can behave like a natural mediator. It's always monomer.
Yeah, this actually is from database. It's not from my lab. But for my alcohol, it's like this. Black alcohol, just this part, this part, this part, yes. And also forms covalent bonded diamonds. If you use like this and black alcohol, you incubate them together for a long time, they will be crispy. Yeah, a lot. Quite a lot. And the color is very dark.
Yeah, when we do that activity study, lactase or gel, then we also monitor it because if you leave it for a long time, the reduction takes. And it's specific.
Plus the polymeritis and
But it is, and you see dark, very dark.
ABTS is not good because it's not stable. But HBT is also not good. HBT does not dissolve in water. At room temperature. The solution is very poor.
Yeah.
So that's why we develop thermophilic lactase. If we use thermophilic lactase, the working temperature is very high, over 80 degrees centigrade. Then we can use a reactor at a high temperature, and the solubility of HBT at higher temperature will be increased. But it does not work at all. I tried. I will present the results in the next tutorial.
Most of the plant chemistry bacteria that produce lactase and bacillus.
Yes, bacillus, yes.
And they live this high temperature also.
Yes.
There is a high temperature and they produce lactase. Then most of the introbacterial family, they also produce lactase. Introbacterial.
Okay.
And their temperature optima is also very high. Their temperature is also very high. So if you want to try that also, we have that.
We have purified and commercialized the bacillus lactase.
Better than bacillus. We have from your seed. It's better than it's supposed to be better. pH which is high alkaline. And it has two isoforms. Can you tell me something about isoforms? Because you have an idea of, because lactases have multiple isoforms, multiple forms of lactase. So the enzyme on which we are working, it might be in one form. In one form of lactase. If you could do the modeling or the docking modeling of all the isoform, then you can easily explain the broad spectrum binding potential of lactase, why it binds to, why it is a very non-specific enzyme which you can regulate anything from pesticide to dye. So that's because of it has multiple isoform. So when you do the docking experiment with different isoform with multiple of these monomer, you may get totally different results. Different binding energy.
Different binding.
This binding is very important.
Yes.
So you need a minimum binding energy is required for to say that binding is better.
So you mean I need to optimize the structure of the model?
Structure, because this structure is from, I think,
For the model.
ICER. It's an online commercial software.
Yeah, online.
From ICER.
Yes.
ICER. It's online. Or it's from use some modeler. There are a lot of software like ICF, International Quality Mechanics, or modeler. Modeler. Or Swiss model. A lot of software. A lot of things I think Puneet knows this thing. You can optimize the model, lot of
Optimize the model.
model because fungal lactases doesn't have good structural database. They don't have good basic database. Because why? Because lactase is very tough. With you don't have lot of, say if you want to, suppose you want to model lactase from Ganderma, you have to use at least lactase which is literally very close to Ganderma. Suppose you are the structure which is a reference for designing a protein model has to be very similar structure. And suppose you are taking a model which is a different isoform, and your one is different because you are making model with a polypeptide chain.
Okay.
So you are having a polypeptide, and you are developing a model with your polypeptide, taking some others protein PDB database as a reference. This is what we are doing. Somebody has done histography. It has a structure of around 1.8, 1.5, 1.9 axon. It has to be a very good structure. And very good structure is not available for all the fungalities. It's not there. One reason for not having structure is lack of copper in active site. When you develop a model, when you do histography, sorry, then it's very important that you don't lose copper from the active site. By histography, by developing your original crystal, but like people, when the histography,
We add with the copy.
this copper has been added in silicon.
Yeah,
And this model has been generated on the basis of the PDB database, which is already available.
yeah, already,
Yes.
already there. We cannot change it.
And some reference is there. So it has to be very close,
Very close.
very close.
Yes.
Otherwise, it can't be predicted properly. Then you have to do simulation. Finally, you need to simulate it. Simulation of
Dynamics.
dynamics. Yeah.
We're trying to do dynamics.
Using Romax.
I didn't do max.
Max.
It took a long time.
It will take around 30 days.
So we spent